This conference will now be recorded.
Good evening, ma'am.
Hello everyone. Today we'll start with a problem. After that, there is one process which is left to discuss under purification techniques. There are total 8 techniques, 7 already discussed, 1 technique is late. So that will be discussed, and after that we will see some examples of extraction of different types of metals from the corresponding ores. This problem is related to Mond's process. Mond's process we have seen in last class. In Mond's process, nickel is purified, but we have to answer that it is purified by using which of these gas. Okay, so there are 4 different options given: carbon dioxide, carbon monoxide, sulfur dioxide, and ozone gas. Okay, so in Mond's process, what we do first, we make some volatile compound of nickel. Okay, and after that this volatile compound of nickel is decomposed again to the metal nickel, and this is the purification method. So this is the process given. First we will take the impure nickel. It will be treated with carbon monoxide gas. So correct option is this one. Now the complex that we are getting is nickel tetracarbonyl complex. The first step is complexation reaction between nickel and carbon monoxide, and the second step is decomposition of this volatile complex of nickel, and ultimately CO is regenerated and pure nickel is formed. So here correct option will be option B. Another question, this is also related to Mond's process. In the Mond's process of refining of nickel metal, impure metal is heated with a stream of carbon monoxide. So that is already mentioned, that we have just seen in the previous question. Okay, but here it is asking which forms are volatile. 4 different types of compounds name are given. All are complex compounds. Okay, so we have to answer which one is correct. Now here we have already seen this is actually the complex. Okay, tetracarbonyl. The first option is given square planar tetracarbonyl nickel. So this is tetracarbonyl, that means NiCO whole 4. And option C, this is also tetracarbonyl. Okay, but here it is square planar. Option C, it is tetrahedral, because when it is tetra-coordinated, 2 possibilities are there. Either it is square planar like this, so all are having 90-degree angle. So this is the positions of the ligands. And another possibility is nickel is tetrahedrally surrounded by 4 carbon monoxide ligand. Okay, but among these 2, which one will be correct, that we have to see. And option B is octahedral hexacarbonyl nickel. Hexacarbonyl nickel means it will be like this, but this is not correct option, because here we have already seen it is tetracarbonyl, not hexa. And the last option is trigonal tricarbonyl nickel. Tricarbonyl means 3CO, but that is also not correct. So B and D we can easily cancel, but among A and C, which one will be correct, that we have to see. Now nickel here having oxidation state 0, which is already mentioned in the options, and when it is 0, its configuration is after argon it is 3D8 4s2. This is the ground state configuration, but if we consider the electronic configuration, 8 plus 2, that means total 10 electrons. 3D, then 4s and 4p. Now we know that when we say that it is square planar, it is basically dsp2 hybridization. But when we say it is tetrahedral, it is sp3 hybridization. So we have to see whether it is dsp2 hybridization or sp3 hybridization. Okay. So here 10 electrons that are basically arranged in this way. Okay, so all 10 electrons now it is present in 3D. Now why these 2 electrons are now transferred here? Because ultimately the hybridization will be sp3 hybridization. Okay, That means this structure will be correct, that is tetrahedral geometry, but not square plane. So correct option will be option C. Okay, sp3 hybridization. And all the 10 electrons, that is both the electrons of D as well as electrons of S, all are now in 3D, and there is no d orbital vacant. So only hybridization that is possible is sp3 hybridization. dsp2 is not possible. And this type of pairing will be possible. It is because carbon monoxide is strong field ligand, though it is completely this concept is from different chapter, that is coordination compounds, and that will be discussed obviously separately. But remember, when it is strong field ligand, there will be pairing of electrons. Okay, so is there any doubt? Both the problems are clear? So only one method is left among that is under purification or defining of the metal. 7 methods we have already seen. Now the number 8 method is chromatographic method. Now when we say chromatographic method, there are actually different types of chromatography possible. But remember, this is obviously one of the methods of purification. Now here by chromatography, basically we are considering column chromatography. So we will use column, and it is useful for purification of elements which are available in minute quantities. Okay, so these are the conditions. Remember, even if the amount is very little, then also it is fine, and the impurities are not very different in chemical properties from the element to be purified. So suppose we have a mixture A plus B, it may be 2, at least 2 must be there, because it we are separating, so one component is not possible, minimum 2, but suppose we have total 3, and among these we want C, and these 2 are impurities. So in this case, the chemical properties of A, B, C, it must be close to each other, otherwise this technique we cannot apply. This method is based on the principle that different components of a mixture are differently adsorbed on an absorbent. In column chromatography, mainly we use silica, and in silica all these, that is the components in the mixture that is present, they will be adsorbed. Now differently absorbed, that means their absorption quality, that is not same for A, B, C. Suppose A is very strongly absorbed or B is moderately strongly absorbed, like this. Because if all of them are strongly absorbed, then it will be very difficult to remove them. Okay, so these, based on this different absorption property, we can separate them. So it will be better if C is adsorbed but very weakly. Okay, now the mixture, it will be put in a liquid or gaseous medium, and then it will be moved through the absorbent. And when we are saying absorbent, it is mainly silica. And look at this picture. So first we have taken the stationary phase, which is nothing but silica. Okay, sometimes alumina is also used, but mainly silica is used, which is basically the adsorbent. So this is adsorbent. Okay, this total portion, there is presence of silica. Now we have loaded the sample. This is the sample which we are trying to separate. So in this sample there must be some components, it may be 2 components, it may be 3 components, and then what we are doing, these components of the mixture are removed by using suitable solvent. Now we have added here a solvent which we are calling it as mobile phase, because it will move. Okay, now when we are we have added this solvent, what it will do, now these 2 components, suppose one is A, another one is B, these 2 components will have different solubility in this mobile phase, and also different absorption in this silica bed. Okay, now see, when that is A, which is the blue part, it is suppose strongly absorbed and it is less soluble in the mobile phase, and B, that is the maroon part, that is more soluble with the solvent. So what will happen? As B is weakly absorbed and more soluble in the mobile phase, so it will come down fast and it will be remaining here. Now gradually with time what will happen? The gap between these two will between these two band it will increase, and finally see this maroon part, it is already separated, that is eluted molecules, and after that suppose it is B, it is A. So if B is desert and we are obtaining it first, then we don't have to do anything about A because A is not wanted. But suppose if A is the desert part, B is the undesired part, then first B is removed and after that we will recover A. Okay, so this is the principle based on which we can separate mixture. Is it clear? Should I repeat it once more? So all the 8 methods we have discussed. Now we will see different extraction of metals from their ores. So the first metal that we have taken here is extraction of iron from its oxide. Okay. So here we have taken this type of arrangement. See here in this arrangement, what we are doing, we have different temperature zone. So if you look at this upper zone, here temperature is very low, around 800. Then the middle zone, it is around 1000 degrees centigrade. And as we are moving down, here temperature is very high. That means gradually the temperature is increasing. Iron oxides are mixed with limestone. So iron oxide is basically the ore from which we are trying to separate iron. That is, we are trying to extract iron. Better we say extract. And for that, what we are doing, first this iron oxide, it is mixed with calcium carbonate, which is also known as limestone, and also coke. Coke means carbon. And this mixture of iron oxide, calcium carbonate, and coke fed into the blast furnace from top. So here we are charging this sample mixture in which we have ore plus coke and CaCO3. We are charging this mixture from upper part. Okay, so first what will happen, the main thing, that is the ultimately what will happen, there will be reduction of this oxide, that is iron oxide will be reduced to iron. But how it is happening, because it is not a single step, there are different steps in different temperature zone. The first step that we are considering, it is basically at the high temperature zone. See here temperature is 2200 Kelvin. That means in terms of degree centigrade it is around 200. That means this temperature zone, that is the last part. Here we have hot air and oxygen, and this reaction will take place here. Lower part where coke burns to give this temperature, because here the reaction is exothermic, so heat will be released. Okay, so this carbon, that is coke, is oxidized by O2 and it is forming CO2. The reaction is also written here. After that, this is this zone we are calling it zone of fusion, because here fusion reaction is occurring. The next zone is zone of heat absorption, where heat will be absorbed, and this zone is basically the middle portion. So in this middle portion where CO2 is rising up, so in the last zone already CO2 is produced. Now this CO2 will be moving upward. Okay, and this CO2, it will combine with carbon and it will produce carbon monoxide. Okay, this is one reaction that is occurring here. And in this zone, other reaction is occurring, which is reaction between CaO and SiO2. Now, where from this calcium oxide is coming? It is basically coming from decomposition of this limestone. Calcium carbonate, if it is decomposed, it will produce calcium oxide and carbon dioxide. This calcium oxide, the purpose of adding limestone is that basically we want to get CaO. Why? Because CaO will react with the impurity silica. Silica is basically the impurity which is present in this iron oxide ore. So as this is the undesired part, we have to remove it, and for that the flux that we are using is calcium oxide. Flux is used to remove the impurity by formation of slag. So this is basically the impurity CaO. It is reacting with SiO2 and we are getting calcium silicate. It will be removed because directly silica removal is not possible. So that is why we are adding this compound flux C calcium oxide, which is basically generated from calcium carbonate. Now here silica, which is the impurity, it is non-metallic oxide. That means it is acidic oxide. So that is the reason the flux that we have taken, that is actually the basic oxide, that is metallic oxide. And if it is the opposite case, that is the undesired part, if it is basic oxide, then we have to use acidic oxide as well. So these two reactions are occurring in the middle zone and in the zone of reduction. Zone of reduction is basically the last zone, that is the upper extreme part. Now Fe2O3, that is iron oxide, which is coming from top, because we have charged this ore, which is nothing but Fe2O3. This Fe2O3, which is coming from top, it will be reduced by carbon monoxide. And where from we are getting carbon monoxide? That is already generated in the middle zone. Okay, so this carbon monoxide, now it will react with Fe2O3 and it will be ultimately reduced to iron. But see, here we have some stepwise, some steps. It is not direct one-step reaction. Fe2O3, which is coming from top, first it will react with CO and it will produce Fe3O4. Now, this is basically reduction by CO. But how this reduction is happening? See, here oxidation state is +3. Okay, and Fe3O4, it is basically mixed oxide. It is combination of FeO and Fe2O3. Just add these two, you will get Fe3O4. Here oxidation state is +2, here it is +3. That means some +3, Fe+3, it is already reduced to Fe2+, but it is not complete reduction, partial reduction. Then this mixed oxide Fe3O4 further reacting with CO, and now it is completely reduced to +2 state from the mixture of oxidation state, that is both +2 and +3. Now it is completely converted to +2. Okay, and finally this is also not the final step, because final step we must obtain the metallic iron. So this ferrous oxide, that is Fe2+ oxidation state oxide, that is finally reacting with CO and ultimately we are getting iron. So this is the actual component, that is substance that we want to get, because it is extraction of iron from its oxide. Okay, so these are the different steps. The first zone, that is the extreme lower zone. This is the zone of fusion, then heat absorption zone, and the reduction zone, which is this upper part, which is comparatively having low temperature. Okay, and all the gases that will be produced, because these are the byproducts. See, there is an opening which is for exhaust gas. Okay, and here the slag that will be produced, that is the undesired part we have to remove. This molten slag, we can remove it through this channel, and iron that we will get, that is the final result, that is actually the pig iron. Remember, we have already seen how we are getting pig iron in previous class. Okay, so from this channel we will get iron. This is the extraction of iron method from its oxide by using blast furnace. So this total arrangement, or if you say instrument, it is known as blast furnace, which can resist very high temperature. Okay, that is the extreme high temperature zone, that is around 2000 degrees centigrade, very high temperature. Okay, so is there any doubt? Should I repeat? Now this extraction of iron, if we see this flow chart, it will be easier for us to remember. So first, here we have this iron ore. We know that in metallurgy the first step is concentration, second step is extraction, and the last step is purification. So the concentration part, that is the first step of metallurgy. Here what we are doing, concentration by gravity process followed by electromagnetic separation. Remember, under concentration topic, there are different methods by which we can do it, and as iron, it has attraction towards magnet, so that is by electromagnetic separation we can do the concentration step. Then in next step, calcination and roasting. Calcination and roasting, this is under extraction of concentration of iron state. So this step is still going on. Calcination and roasting, what we are doing in presence of air and heat, moisture, CO2, SO2, all these undesired impurities are removed, and FeO is oxidized to ferric oxide. That means Fe2O3. Next, this Fe2O3 smelting in a blast furnace. Blast furnace, remember the last slide, the picture that we have seen. This process is also known as smelting, which is nothing but reduction. Okay. So here what we are doing, we have charged this mixture, ore plus carbon, that is coke, plus limestone, that is CaCO3. So first, that is here all the steps detail if we see. Calcium carbonate 1000 degrees centigrade, remember in the middle zone, CaO is produced, and this CaO is reacting with impurity, and finally it is making this slag. Okay, and CO, it will, that is in presence of hot iron, it will be converted to CO2 and C, but actual reducing agent is basically CO. Okay, so there are some impurities also. These reactions are not shown in the previous slide, and these are not very important also. Just remember, these are the undesired part. Okay, so finally the iron that we are getting, that is basically this spongy iron. Okay, so this is the main reduction step. The iron which is obtained from blast furnace, that is known as pig iron. Okay, and why it has specific name, because after this pig iron you will see that further purification is done, then there is another name, and different carbon content is there. So when we are saying it is pig iron, it is basically containing 4% carbon. That is, still there is some impurities present. It is not that 100% pure. And also some other impurities like sulfur, phosphorus, silicon, Mn, manganese, etc. Okay, so all these you can also see here. These elements, they are compounds. That is, SiO2 is impurity, MnO2 is impurity, P4O10 is impurity. All these are basically reduced in presence of coke. Okay, because we have added coke, and these are converted to the zero oxidation state, but still these are present as impurity. Okay, so these can be molded into variety of shapes, that is this pig iron, and from pig iron we are making cast iron. How we are doing this? Cast iron is made by melting pig iron with scrap iron and coke using hot air blast. That means cast iron is comparatively more pure. If we compare with pig iron, it is comparatively more pure, and it has slightly lower carbon content. That means the carbon content, previously it was 4, but now it is 3. So obviously it is of different quality. Both are iron, but different names are there because it is depending on the carbon quantity and other impurities. So in cast iron, which we are getting from pig iron, it is comparatively pure, and remember, it is extremely hard and brittle, not like pig iron, which is basically spongy in nature. Fine. Now after cast iron, there is another type of iron which is wrought iron. Now this wrought iron or malleable iron, this is actually the purest form of commercial iron that we see. So wrought iron is made from cast iron. How it is done? Cast iron is oxidized. It is prepared from cast iron by oxidizing the impurities. That means the impurities that are present in cast iron, these are oxidized in reverberatory furnace lined with hematite, and here what happens? This reaction is occurring. Okay, so the carbon, that is remaining carbon impurity that is present, it is reacting with this hematite, and this carbon is converted to CO. That is, carbon is basically now the impurity, and we are removing this impurity by converting it to oxide, and Fe2O3 is converted to iron. Now the carbon content is further reduced now from 3%. Remember, in last slide we have seen carbon content in cast iron is 3%, but now it is reduced to 0.2%. So that is, it is a purest form because it is almost 99.9% pure. Okay. So first there is pig iron, after that cast iron, and finally it is wrought iron. Limestone is added as flux, and remember, from limestone, basically after decomposition it forms calcium oxide and carbon dioxide. Calcium oxide is actually the actual flux, and sulfur, Si, phosphorus, all are oxidized and they are converted into slag, because flux plus impurity equal to slag. Now we will see some points of difference between pig iron and cast iron. It is obtained from chemical reduction of iron ore, which we are doing in blast furnace. But cast iron we are getting from pig iron. So first pig iron, then cast iron. Its melting point 1200 degrees centigrade. It is to some extent high. It is more brittle, it is less brittle as compared to pig iron. It has more carbon content, 4%, but here it is 3%. Next, it is not suitable for making useful articles because it is more brittle. It is suitable for making useful articles. That means if we see from application point of view, cast iron has more application. It is produced in blast furnace, but it is produced in cupola furnace, which is obviously a different method. Details not required, just remember the name. And it is less suitable for engineering applications. So from application point of view, it is not so important, but it is suitable for engineering applications. Okay. So these are the difference between pig iron and cast iron. Any doubt? Now we will discuss this problem. Among the reactions A to D, 4 reactions are given, A, B, C, D. Okay. Among these 4 reactions, the reaction or reactions, that is, it may be one reaction or it may be more than one reaction, that does or do not occur in the blast furnace during the extraction of iron is or are. That means if you look at the options, in option 1 and 4, you have only one equation. But if it is option 3 and 2, it is CD and AD respectively. Okay. Now we will consider one by one these reactions. CaO, SiO2, it is producing calcium silicate. And we have to find those reactions which are not occurring. But this reaction is actually occurring because this is the flux. And CaO is basically generated from CaCO3, limestone. This flux is reacting with impurity and it is producing this slag. So this reaction is basically occurring. Okay. Now, if you are sure about A, then you can easily cancel out option 3 and D, because in option 3 and 4, option 3 and 4, not D, we do not have A. Sorry, what I'm saying. A is basically occurring. So this cannot be correct option because we have to choose those reactions which are basically not occurring. So A is basically occurring. So this cannot be the correct option. But if A is not correct, then option 1 and 2 also not correct because here we have A. Next reaction is Fe2O3 reacting with carbon monoxide and it is converted to mixed oxide Fe3O4. Now this reaction, remember, we have seen, okay, because Fe2O3 where oxidation state is +3, now it is converted to both +2 and +3. So this is partial reduction and this reaction is also occurring. So it cannot be correct option. That is B, where B is present, it cannot be correct. Then FeO and SiO2. Now FeO reacting with SiO2 and it is producing FeSiO3. This impurity we do not remove by FeO because FeO is actually the desired part. From FeO, ferrous oxide, what we make? after reduction we get iron 0. So this cannot be used as flux and this reaction doesn't occur. So this will be correct option. Okay, and C is basically present only in one option, which is option 3. So that is why option 3 will be correct option. But it means that D reaction, that is also not occurring. See, in reaction D, what is happening? FeO, it is directly reduced without any external reducing agent. So as if it is self reduction, but it is not possible, and this type of reaction also we have not seen in the blast furnace. So this reaction is actually not occurring. So this will also be the correct option, because we have to choose those reactions which are not occurring. So this type of reduction is not going on, because this reduction is occurring in presence of reducing agent. Okay, it may be carbon or carbon monoxide, both can be used as reducing agent. So this reaction is also not occurring, and correct option will be option 3. Okay, so you have to read the question very carefully, because if you just miss this note, then probably we will choose wrong options, because then we will choose those options which are actually occurring. But here it is asking those reactions which are not occurring. Okay, should I repeat it once more? Is that fine? Next, extraction of iron from its oxide. Again the same topic, but now why it is different. Here we have the Ellingham diagram. Okay, and from this Ellingham diagram we can understand that among the reducing agent, there are two types of reducing agent possible. One is carbon, that is coke. Another one is carbon monoxide, which will be better reducing agent and which temperature will be suitable for this reduction. So in Ellingham diagram, what we do, we take del G value in the y-axis and temperature in the x-axis. Now from this we can predict whether this reduction is possible thermodynamically or not. We cannot get any idea about the kinetics of the reaction, that is whether the reaction is occurring at a very high rate or slow rate. That is not possible to predict, because it is all about thermodynamic concept. You just can predict whether this reaction is possible or not. Maximum you can predict, but not about the rate. So here we will see that how thermodynamics is basically helping us to understand why coke reduces the oxide and why this furnace is chosen. Because in this furnace there are some specific temperature zone. Okay, remember 3 temperature zone: low, high and moderate. Now one of the main reduction step we have seen in this process, which is FeO, that is ferrous oxide, is reduced by carbon. So from +2 state, now it is 0. Now here S and L both physical state are mentioned. That means it may be in liquid form or solid form. Now this reaction can be broken in which in two simpler reactions. Okay, that is the half reactions if we consider, because here C is oxidized to CO and iron is reduced to iron oxide is reduced to Fe. So two reactions are going on. So if we break this total reaction in two simple reaction, then we will see this. We can get these two reactions. Number 1, number 2. FeO, it is reduced to Fe and oxygen is removed, and carbon is reacting with this oxygen and it is oxidized to carbon monoxide. Now carbon plus half oxygen and conversion to CO, that is actually this line. Okay, that is for reaction equation 2, this line we have to consider. And for the other reaction, that is conversion of FeO to Fe and oxygen, this you can find here, that is this one. But remember, that is the reverse equation, right? Now as it is reverse equation, so at any temperature, suppose if you choose this temperature, which is basically around this, suppose I am choosing this dotted line, okay, which is at 1400 degrees centigrade. Now at this temperature, if we extend this line, it is cutting here, that is the iron equation 1 line, it is cutting here, and for carbon line it is cutting here. Now the corresponding del G values, it is minus 445 almost, and this one is minus 341, but as it is reverse equation, so we will take the opposite sign. That means we will take positive sign. Okay. Next, as by summing these two equations, you get this equation 3. So that means if we add these two del G values, we can get the overall del G values. Now this overall del G value, it must be negative, then only the reaction will be spontaneous. So see, when it is around 1400 degrees centigrade, the corresponding del G values for this reaction, it is minus 341, but we will take the positive value because this is the reverse reaction. And for other one, it is minus 447. Okay. Now if we add these two equations, you are getting this equation. Then you can take 2 common, both side it will be cancelled. So this is the final equation, and here del G value is minus, as we have that is to cancel from both side. So just divide 106 by 2 and it will be minus 53. So ultimately the del G value is negative. So that is the reason this reaction is spontaneous. And there is a simple trick by which you can easily predict whether this reduction will be possible or not. See, if you find the point where these two lines are cutting each other. So this is the point if these two lines are cutting each other. Now, if we move towards left hand side, this light blue line, it is below this navy blue line. That means what? Here, Fe will be acting as reducing agent. Okay. But if you are moving further this point towards right hand side, now this line is below the line of iron. That means now carbon can act as reducing agent because this line is below the line which is below, the corresponding pieces can act as reducing agent. Okay. So that is the reason if it is asked that why carbon, when it is used as reducing agent, it can act as reducing agent only above this temperature. That is, this temperature means it is around 800 degrees centigrade or 1073 Kelvin. So only if the temperature is greater than 1073, then only carbon can act as reducing agent. Otherwise, if you consider carbon monoxide as reducing agent, not carbon, carbon can reduce greater than 1073 Kelvin temperature. But if it is carbon monoxide, see, now you have to consider this black line. Now this black line, it is below this blue line, light blue line for iron, below this temperature. Okay. But if it is above this temperature, then this sky blue line, it is below this black line. That means now carbon monoxide cannot act as reducing agent. So for carbon monoxide, if it has to act as reducing agent, the temperature must be below this temperature. Now this is around just in between 1000 and 1500. So suppose it is 1250 degrees centigrade. So only below this temperature, carbon monoxide can act as reducing agent. That means if you are using carbon as reducing agent, temperature must be high. But if it is carbon monoxide, low temperature is fine. Okay. Now just have a look in the blast furnace picture. Here what we have seen. When it is reduced by CO, basically it is occurring in this middle temperature zone. That means it is between the temperature 1000 or 1300 degrees centigrade. So it is around 1250 degrees centigrade. Okay, this type of reaction is possible. But if it is the reducing agent is carbon, then the temperature must be very high. Is that clear? The principle that we have discussed in the Ellingham diagram, is there any doubt? So now we can answer the question why different temperatures are required depending on what type of reducing agent you have taken. That is it directly the coke, that is carbon, or carbon monoxide? So depending on the reducing agent, temperature will also be different, which is clear from this Ellingham diagram. Any doubt? Should I repeat? So we have finished iron extraction from its oxide. The next metal is aluminium extraction from its oxide. Now here, for reduction purpose, that is, reduction means it is basically the isolation step. The first step is concentration, then isolation, then purification. So concentration step we are not discussing, we are discussing the middle step, that is second step, which is isolation. That means from oxide you will get the metallic aluminum. And the process that we are using is known as, there is a specific name, which is Hall-Héroult process. And you have to remember these names for each metals. There are different processes, different names, because in question you will be getting a question like this, that the process of extraction of aluminium, what is the name? Okay, or it may be asked in a different way, that in Hall-Héroult process, which metal is extracted? Now there will be different options like aluminium, iron, silver. Okay, so correct option will be aluminium. So we have to remember the name of the specific processes. So this process is electrolytic reduction. So here we are using, we are also doing reduction reaction. Remember, in case of iron, in blast furnace also we have done reduction, but that is different types of environment. There we are using carbon or carbon monoxide as reducing agent. But now for aluminium, which is very more electropositive compared to iron, so we cannot use the previous method. Now the method is different because aluminium is more electropositive, and for more electropositive metals, extraction method is also different. Now we have to do electrolytic reduction. Okay, that means electrolysis we will do. Here we will use some electrical energy to do some chemical reaction. The process is used in the extraction of aluminium, and here the ore that we are using is alumina, Al2O3. Now this Al2O3 from which we are trying to extract aluminium, it will be mixed with cryolite. What is cryolite? Cryolite is Na3Al6. Now what is the purpose of using cryolite? Remember, this is a question from this related to cryolite is already there, that it will be asking that what is the purpose of using cryolite. Okay, so the purpose is to decrease the melting point of the mixture. The result is lowering of the melting point of the mixture. That is the purpose of adding cryolite, and in turn it increases its ability to conduct electricity. Okay, remember, this is the purpose of using Na3Al6, which is also known as cryolite. Then we will see, now come to this picture. Here we are using carbon as anode, and in cathode also it is carbon. Now here the cathode, normally in electrochemistry, the picture of electrolysis that you have seen, you will find it here somewhat different. Okay, but see here the cathode, it is not rod-like nature, it is basically carbon lining. So this part is basically the cathode. Okay, see, and all these are anode. I am writing. Now both cathode and anode, both are made of carbon. Okay, next, in this electrolyte mixture, we have taken this alumina, which is mixed with cryolite. So this is the electrolyte, and finally what is happening here, in the cathode there will be reduction reaction, which is acceptance of electron by aluminium 3+, and it is converted to aluminium 0. And in the left hand side, that is at anode, here oxidation is taking place. So carbon is oxidized to CO2 and it is releasing electron. These electrons are actually accepted by aluminium 3+. So anode is always oxidation and cathode is reduction. Now we will see the reactions. At cathode, first we will see anode, because in anode O2 minus ion, it is basically generated from aluminum. Now this O2 minus ion, if it is releasing these electrons, it will be now converted to neutral oxygen atom. Two neutral oxygen atom together will make O2, and carbon, which is basically the carbon anode, this will react with this oxygen and ultimately it will produce gaseous byproduct. See, both are gaseous in nature. So it will be very easily removed. So that is the reason we have taken carbon as anode, because here the byproduct that is obtained, it will be reacted with carbon and it will be removed in the form of CO or CO2. And now come to cathode, where reduction is occurring. Here Al3 plus ion, which is basically generated from Al2O3, it will accept 3 electron and it will be converted to liquid aluminium. That is the molten aluminium. See, this is the molten aluminium. Now, what is the overall reaction? You have to add these two individual reaction, and obviously after making the electron same, because here it is 3 electron, it is 2 electron. So both electron, we have to arrange the half reactions in such a way so that the electron number is same. Then when you will be adding these two reaction, electron will be cancelled. So the overall reaction is alumina in presence of C, carbon, it is converted to metallic aluminium. The aluminium metal which is obtained by this method, C, it is very pure, 99.5% pure. So here the fate of carbon, which is the carbon anode, it is oxidized to CO. As corrosion of graphite rod means this carbon rod in the anode, it occurs because gradually the carbon is consumed. So there will be corrosion of graphite rod. So that is the reason after some time we have to replace it periodically. Okay. So is there any doubt? Next is extraction of copper from its ore. Again, we have taken oxide. So first we have seen Fe extraction, then aluminium extraction. Now the third one is copper extraction. Now for copper extraction, here we have the Ellingham diagram. Here different lines are present, but you just have to focus on this line. Not all the lines, just focus on this one, which is the line for copper oxidized to CO2O, and the other line that we'll consider is carbon reacting with O2, it is converted to CO. Another line is this one. Okay, here CO is converted to CO2. Now see the lines of CCO and CCO2. That means this is CCO2, this is CCO. They are at much lower position in the graph, particularly after 500 to 600 Kelvin. Now after 500 to 600 Kelvin means after around this range of temperature, if we see this line is much below this copper. Okay, that means these two can act as reducing agent when temperature is greater than 600 Kelvin, rendering it easy to reduce oxide ores of copper directly to the metal by heating with coke. Okay, but if it is carbon monoxide, which is a reducing agent, now see this line, it is below, but here it is already merging with this one. That means CO will not be very good reducing agent here. Carbon will be better reducing agent, because here gap is also very high, because it is not just only necessity that it must be below the line, but it has to be, the gap between these two lines should be very high, because higher is the gap, higher will be the negative del G value. Okay, so this is the thermodynamic principle based on which extraction of copper is possible. Next, now the actual processes that are done for extraction that we see. Most of the ores of copper are actually sulfide ore. It is not oxide. But sulfide ores can be roasted or smelted, which is basically the conversion to the oxide form in presence of oxygen. Now this oxide, it can be easily reduced to metallic copper by using coke. Remember, the Ellingham diagram that we have seen there, we have already understood why carbon is better reducing agent. So finally it is converted to metallic copper. Now in actual process, the ore is heated in reverberatory furnace where the copper pyrites is actually taken. Now copper pyrites is basically CuFeS2. It is sulfide of two metals, Cu as well as iron. Actual process, what we take copper pyrites. We do not take directly copper sulfate. Okay. So CuFeS2, what is done? First it is converted into the mixture of FeS and CuS. Okay. And this CuS is known as copper matte. So this is the reaction. We have taken copper pyrite, CuFeS2 in presence of oxygen. Now these are converted to the corresponding sulfide salt, and sulfur is removed in the form of SO2 also. Now this FeS in presence of O2, it is converted to FeO, though our main concern is about copper because we are discussing extraction of copper, not iron. Okay. And Cu2S, that is also converted to oxide. Now this copper matte, which is the sulfide salt of copper, it is then charged into silica lined converter. Some silica is also added and hot air blast is blown. Now what is the purpose of adding silica? Silica is SiO2. We are adding this SiO2, it is actually acting as acidic flux because here we have this impurity which is metallic oxide, and as it is metallic oxide, it is basic in nature. So if you want to remove this impurity by using flux, flux must be acidic. Then only it can react with this basic impurity. Ultimately, it is producing FeSiO3 slag. Flux plus impurity, or it is also called gangue, it is producing slag. Now the solidified copper obtained, that is obtained finally, that is this solidified copper, it is having some appearance of blistered appearance. Now why it is having blistered appearance? That is some bubble, as if some bubbles are formed on the surface of copper. It is because here SO2 is also removed in the form of gas. So that is the reason some bubbles will form and there will be generation of some blister. And that is why it is known as, that is the final copper that you are getting, that is known as blister copper. So here the reactions are FeS reacting with oxygen. This is same reaction as you are seeing here. Then removal of this impurity or undesired part by using acidic flux SiO2. Then Cu2S in presence of oxygen, it is converted to oxide. Now this oxide, it can be reduced by carbon, or another way which is can also be done is self reduction. So in self reduction, what is done? Some unreacted Cu2S, it will react with Cu2O and finally it is converted to copper and SO2. So see, this is the blistered copper, because here you can see formation of some bubbles like formation, and all these are basically the reason is because SO2 is generated as byproduct, which is gas. Is there any doubt? Now one problem. This is related to both Hall-Héroult process, which we have discussed for aluminium, and also related to copper and iron. The correct statement we have to find. There are 4 statements, 3 will be wrong, 1 will be correct, because it is single correct choice answer. Leaching of bauxite using concentrated NaOH solution, it gives aluminate and sodium silicate. Now leaching process, that is discussed actually at very first of this class, where this leaching is basically under concentration of ore, and there we have used bauxite, which is having that main component is alumina, that is the ore of aluminium. And in leaching process, what we do, we take NaOH and it gives us sodium silicate and sodium aluminate. This is actually correct. Okay, because see, these are the schemes that is actually happening in leaching process. So this is leaching process. And here we take NaOH, water in presence of 473 to 523 Kelvin. This type of complex of sodium produced. Now it is written sodium meta-aluminate, but sometimes you will also see it is written as sodium aluminate. Both are actually correct. So when it is sodium aluminate, it is basically having formula NaAlO2, and this is actually the anhydrous form of sodium meta-aluminate. Just remove water from this molecule, you will get this molecule. So this is the anhydrous form, this is the hydrated form, but both are fine. So here it is mentioned that it is giving us sodium aluminate and sodium silicate also. So this NaOH is also reacting with this impurity and it is forming sodium silicate. So this statement is correct. This is true. Okay. Next step, that is all the other three statements will be wrong. But we will see why it is wrong. The Hall-Héroult process is used for the production of aluminium and iron, but it is used only for iron, aluminium, not iron. So that is why this statement is not correct. Then pig iron is obtained from cast iron, but this is not correct. The reverse statement is correct. So first there is pig, then cast, and then wrought iron. Okay, so pig iron obtained from cast is not true. Cast iron is obtained from pig. So this is also wrong. And the last statement, the blistered appearance of copper during the metallurgical process, it is because of the evolution of CO2. But it is not because of evolution of CO2, because here CO2 is never generated, right? Here this blistered appearance, it is because of evolution of SO2. So this statement is also correct. Incorrect. So correct option will be option 1. All these are not correct. Okay. This is the blistered copper picture. Another question. In the Hall-Héroult process, aluminium is formed at the cathode. That is correct. Cathode is made out of which element? Pure aluminium, copper, carbon, platinum. It is actually carbon. Remember, both anode as well as cathode, both are actually carbon. And here it is taken, this carbon is taken as anode. There is a special reason for that, because this carbon, it will react with the side product which is O2, and it will form CO and CO2, which can be eliminated very easily. So that is why option 2 is the correct option. Okay, is there any doubt in the problem? Now the fourth metal, it is extraction of zinc from zinc oxide, but it will take time, so better we will discuss it in the next class. So today we have seen extraction of 3 metals, right? One is iron in blast furnace by using carbon as or carbon monoxide as reducing agent. Then aluminium in Hall-Héroult process, which is basically electrolytic reduction, where we are using electrical energy for the reduction purpose. And the third method is copper, how we are extracting copper from its ore. Okay, and mainly that is in practical cases we take chalcopyrite, that is CuFeS2, and here iron is removed because here iron is not the desired part. Okay, so regarding all the slides, is there any doubt? Okay, so we will end the session here. Thank you for listening.